large files. That's always an interesting one. So I work as an engineer at PSPDFKit, as Joe said, and I work on a PSPDFKit server, which is, surprise, surprise, an application that you can use to manipulate PDF documents. The main thing about this is that PDF files have, if you have, I assume that everyone has dealt with one PDF files before from a user point of view. Depending on what PDF file contains, it can be anything from 20 kilobytes, like for a very simple piece of text, to 1+ gigabytes, even 2 if you get like some specific type of files that are usually generated for printing from other Adobe programs and things like that. So at the end of the day, PDF file is pretty much a key value store in disguise, where the keys can be pretty much like any type of kind of like string, and then the values can be whatever you want. And so they're can be extremely complex and expensive to render depending on what they have inside, and then they sort of have all sorts of other problems because the spec is not really a spec. It's more like a reference that you have to interpret, and you could sort of like have a lengthy conversations about, which luckily are not the scope of this talk. The scope of this talk is around essentially things that ended up sort of like looking at throughout time throughout this project, working on this application. Some of them like building them, some of them like taking them over and they were existing there, and some of them sort of like banging my head a little bit against the wall in terms of like solving some of these problems. The problem space and the operations that I sort of like want to talk about as part of this talk, which will have basically 3 examples along these 3 topics, are upload and retrieval, so like essentially fetching files or writing them from potentially remote sources, where it could be anything from an S3 endpoint, writing them inside a DB if appropriate, or interacting with them through an HTTP interface, performing, let's say, intensive operation, even if performing a SHA on the file is not necessarily the most intensive thing that you can do with it, but it is a CPU and IO bound operation primarily. And basically management of file system based caching. So like you got a large file that is fetched from a remote source, you don't want to fetch it every time you need it. You want to cache it in the file system as close as possible. Like when it comes to like 500 or 1 gigabyte of files, keeping it in memory may become problematic, especially if you don't have control over the infrastructure, which is which is our operational constraint. We don't host our application. We build it and then give a Docker image to our customers to run, and so they can run it depending on what they have accessible to them in terms of and what their catalog of files looks like and the document types look like. They could have like, you know, a couple of gigs of RAM or 4 gigs of RAM or 64 or whatever needed to support their workload. So the dangers and the perils, I should say, essentially revolve around like sort of like 2 things really, but with a slight difference in them. Well, one is obviously memory starvation. Like you basically consume memory very fast, run very fast operating on large files if you're not careful. The other problem connected to that is irrespective of how much memory you consume, if it leaks, like if you take memory and don't release it for whatever reason, then over time the node basically ends up saturating available memory and then just crashes. And then depending on how much concurrency control you put in place, and potentially CPU and IO starvation kick in, meaning you either read and write too frequently from the file system beyond what the file system is able to, or beyond any limits that might be imposed by your infrastructure. And the other thing for complex files and for operations that require, for example, rendering, require CPU, you might just burn through the available CPU capacity you have. For example, there are cases where if you deploy an AWS with CPU credits, you just like burn them through very quickly, and then you can't do anything afterwards. The scope of this talk is, starting from those problems, like we're going to look at some of the issues, and we're going to look at how to identify the symptoms of them and how sort of like what to look at and provide some solutions for it. However, we're not going to try to find a one-size-fits-all kind of solution, meaning here's how you can solve everything. And if you have that, implicitly you could package all of this in a library. I don't think that's necessarily possible, though I would like to be proven wrong in that respect. But I think it's more important to understand the principles, because none of the things I'm gonna sort of like show are particularly esoteric or particularly like unseen before. It really is just putting some pieces together and looking at certain specific properties of what we're doing to make sure that everything is on track. So the principles are more important than the code, effectively. So the first example is reading files. So I've seen this pattern a few times before, and somewhat like circulates in examples online as well. But you want to basically provide access to somewhere in a file system to a controlled interface that is somewhat configurable from a specific starting path, like a directory where these files are, and then mediate this through a process interface, so with a gen server that basically knows where the path is and gives you access to the content of these files. It's not necessarily the way I would recommend to tackle a problem like this, like mediating access to a directory and then managing that. But it is a way that I've seen used before, and in some cases, it's just a solution that you can find in place or you can come up with. So at least from the point of view of understanding the implication of that design, it's worth like going through what happens if you don't pay attention or if you don't look at certain possible pitfalls in that respect. So this version of the code on screen, which is basically just the interesting part of a gen server that does what we set out to do. You can read a file name to a call, and then in the end of call we join the file name we requested with the base path where the file is supposed to be, read the file contents, and pass them out to the caller. So from that point of view, there's nothing particularly complex about this. In fact, it's so straightforward that the entire implementation fits comfortably in a single slide. However, let's try to basically profile this a little bit. So how do we test this profile? We basically check the total memory, at the start, read the file, check the total memory again, and then run basically a function out of the recon package, which I'm going to link at the end of the talk. But essentially, it's a diagnostics package maintained by Fred Hebert, and I really hope I got the surname pronounced correctly, but probably I didn't. It's a fantastic package that you can drop in using production. It has like it has like tools to diagnose potentially problems around resources usage, tracing, and a bunch of other things you can use. So we're going to look at the binary leak function, which basically measures, essentially tells you before and after a garbage collection round, which processes have essentially released binary memory. And so we see if the cache process that we have up is one of those processes that leaks. So the code for that test is roughly this code. I mean, roughly it's exactly that code. This large file is 128 megabyte files, just to have an order of magnitude. And then we just look at the processes out of the binary leak, and we see if the one that we have, the one named with Perils examples cache, is one of them. So if I run this on just like an empty Elixir project that really has just the code shown before and this example, we have basically, this is roughly 30 megabytes this is 166, but a little bit, like roughly the difference suspiciously is close to the size of the file that we have, and the delta shows that the cache process, when you run binary recon bin leak, reports 2 references collected from this process. Means this process released, after garbage collection, released 2 references to the binary. So what did this mean? Because the process read the contents of the file inside the handle code, so it did it inside in process, and that binary size is beyond 64 kilobytes, then the binary is reference counted. It's not kept in the heap of the process, in the memory of the process, but it's reference counted. So because the process is still alive, our cache process, and it doesn't do much work. Like it just didn't do much. Like it gave a file. So it's not a process that has a lot of work to do, and then it didn't. In particular, in this use case, it does have a high frequency of access, which is common for a lot of applications that don't do much work in that respect. Like anything that doesn't really, do much in that respect, not a high traffic application, there's a chance that the process doesn't do a lot of work. So it doesn't essentially do enough to trigger the garbage collection. So it holds these references, and then they don't get garbage collected. And the problem is that this represents, like, over time, potentially a risk of filling up RAM just because the garbage collection is not triggered. So how do we solve this? The one possible recommendation is to, instead of returning from the handle core just the contents with the standard gen server reply, is to hibernate the process. Hibernation basically makes the process dormant, runs the garbage collection on it, releases the references, and then the process is still alive. It is reachable, but to reach it, it requires basically to get out of hibernation, which gives you a little bit of CPU cost to pay. So you trade essentially memory safety for a little bit of CPU cost. That's okay most of the times. To me, what I would recommend as a change is that I would not basically read the file in the process. I would change the pattern. Normally, reading essentially expensive files for a one-off operation. So if you want to work on that content, or if you need to pass that content somewhere, there's normally different ways to do it. If you have to give that back through an HTTP endpoint, there are built-in ways that you can send the file directly. There's a plug function for that, for example, if you wanted to, just by knowing the path. Or if you want to operate on it, it's much better to read it inside a process that has a limited lifetime. So if your process, for example, a request process, starts, handles the request, and terminates, that will automatically, basically, once the process is done, the garbage collection happens as the references are released anyway. So changing the signature to return the path, for example, and read the path in the calling process might be just a better architectural choice in that respect. So processing files. So the second part, now when we have a file, we want to do something with it. So we want to basically, in this case, we want to calculate the SHA of the file. So this is just one thing that you can do with a file. You could do anything with it. You could run a word count inside if you're processing text or anything like that. Really, that's just the domain logic situation in that respect. It becomes something that you need to decide what to do. Again, one slide implementation. You essentially read the file again. This doesn't happen in a specified place in our application. It's not inside a gen server or anything like that. It's just a function on its own. So we read the file, we hash the contents of the file, and we encode them base 32 just to make them essentially readable, so that you can, I don't know, put them in a URL or write this somewhere where it becomes human readable. So the test for this is very similar, and then we're going to focus again on seeing memory usage for this, essentially. So from this point of view, the problem is not really, like, if you look at the code, essentially we do the same thing. So if you look at the results, the problem is not necessarily that nothing leaks, because the process that we're using doesn't even, there's not necessarily a leak, because the process doesn't stay alive, or rather, the process stays alive as long as we run that code. But the size of the memory goes up essentially for the same, in the same size, the size of the file, and that's not necessarily something that you want, even if the garbage collection, even if we trigger it in this case, which is something that would happen normally, it doesn't really mean that we have to basically do it like this, because by ballooning for the memory with the size of the file, we essentially limit our ability to do this SHA operation concurrently, because we can do less of them. If we have 10 large files and all of them take up 1 GB of memory, which is not this case, but as a sake of argument, it means that we need at least 10 GB to be able to process 10 files at the same time. So that looks like this. If you had to, like, this is a screenshot of the Observer application, but that looks like this. The memory just goes up, and you know, it stays up because in this example I haven't run, in this screenshot I haven't run garbage collection after this. But if you did this in a temporary process, you will see that going down. The fix here is to use file stream, which is mentioned a few times as a way to process files and read files lazily, but so that we don't really use too much memory. But normally, most of the examples I've seen them a lot when it comes to processing text or counting words or doing this type of work. You can actually use it to do anything really, like you're just reading files. So in this case, a slightly more complicated implementation of the function means that we read basically 8 megabytes, a chunk of 8 megabytes at a time of the file, and then through the stream, and then basically reduce on the stream, and then one chunk at a time update a digest that basically keeps updating depending on, like, with the chunk. And so this value basically, once you finish the file, can be finalized. All of this is all built in a crypto module in OTP, so in the standard library. So you can basically use it straight out of the box. The result is identical, like you get exactly the same hash, but when you run that, the behavior memory-wise is completely different. You never go, you basically, you don't even need to worry about potentially having to garbage collect, because the memory didn't essentially go beyond a certain quota and went mostly back to where it started from. The chart for this is a little bit of a bump here, and then if I ran garbage collection afterwards, and like after the slope, it would go back to the beginning. But we see that to do the exact same thing with a absolutely comparable performance, because the execution time is the same, you consume way less memory. So doing this with that implementation just gives you more bang for the buck. You will be able to run much more of this SHA processes at any given time. You would have more concurrency. At that point, you would need to worry about having enough CPU to do it, or not exhausting I/O in terms of reading from the file system too much. So that the other concerns come into play, but you wouldn't get this problem with memory. The third problem that we want to look at is writing basically things to the file system. So this is another thing that you might do with a cache store, or if you want to temporarily manage temporary files. Like writing temporary files is not something that is, depending on what you do, you might not have to worry about it at all. Like if you, I don't know, if you upload a file to a controller through Plug and Phoenix, Plug does that for you. So you normally don't have to do this. But in our case, when we fetch files and we have to manipulate them, or like pass a file to a transformation and then get a file back to work with. For example, if you rotate pages in a document or anything like that, you deal with all the temporary files. So the simplest thing to do this, and this is just an example which I think is common enough, is fetching from a remote HTTP endpoint. For the sake of argument, and just to keep the example extremely easy, I'm using the built-in HTTP client that comes with OTP. HTTPC is not it's not particularly full featured. I think it's okay for examples or very confined HTTP usage. You might use something else in production, but it has enough features at this point that it can be used to demonstrate the problem at hand. So in this implementation, you basically take the file in its entirety and then take the body and then write it directly to a file. So the flow is basically fetching everything, keep in memory the body, and then write the contents to the file. So don't have necessarily a script for testing this because it really is 2 lines. This is a 12 megabyte file that is just from one of our examples. It's a PDF file, 12 megabytes. So 12 megabytes is important to keep it in mind. And that just does almost 350, 375 memory megabytes of RAM taken just to do those 2 lines of code. It goes down pretty quickly, but the spike is extremely high. Now, honestly, I don't know if it's something that is due to the implementation inside HTTPC, or I don't know if it's specific to a specific HTTP client, but I ran this a few times and it would sort of like ends up averaging between 300, 350, 375. So the peak is repeatable with the library. Another library might have different performance behavior. But my general point is that this kind of things need to be measured. You wouldn't think, or I wouldn't think, that for the 12 megabyte files I would observe a peak like that, but that's what it is. So what's a better way to do it is, because we are dealing with HTTP and a lot of storage systems allow nowadays to do that, is streaming the contents back. So streaming them to the file that we want to write. HTTP has a built-in way to do it. There's an option here that you can use for stream where you can pass a file name and it will do that. But I wanted to sort of like pretend that doesn't exist because I wanted to sort of like show a slightly more complicated way to solve it that ends up being, generally speaking, more flexible. Because a lot of streaming interfaces in OTP, especially if they are, if they come from a, if they haven't been built for Elixir specifically, if they use interoperability with Erlang, they use a lot of message passing to represent the streaming interface compared to, for example, a stream that you could have in Elixir if what you're doing is native to Elixir. So it's useful to just know how to structure that because it's very much reusable. Like worst case scenario, you have messages. That seems that's always the lowest level interface that you can find. So opening a streaming, so an async streaming interface to stream that file gives you back a reference. With that reference in mind, we can basically start a streaming loop, which is a receive loop, where you wait for the beginning of the stream, matching on the reference so that you are sure that you're processing a response for the request you opened. We open a file directly for writing. I'm going to talk about raw afterwards. And then we enter a write loop. The after block here is necessary because if we try to receive and nothing happens, say that the remote server doesn't respond, at some point after 5 seconds, we time out. Without this, we would block forever. The write loop is very similar. We just keep receiving chunks, so it's recursive. It keeps receiving chunks until it receives an end of a stream. And when we receive a chunk, we write it to the file. So this is direct write to the file. So we write the chunk to the file and it's going to keep appending. If if after 5 seconds we don't receive anything, so if at any point we basically time out for 5 seconds, we close the file and return an error. And when we receive the stream at the end, we close the file. Emphasis on closing the file. This is quite a common source of bugs when you do this type of work with file open, is forgetting to close the file. The memory usage of this is much better. Like the total memory usage goes up. Most likely this delta is the size of the streaming buffer, because all of that can be controlled by, there's a few options that you can control both at the HTTPC level and then TCP level that would essentially decide how much buffer you want to use, but that's pretty much that amount. So the operation gets completed quickly, and the memory usage is much lower, so we're doing now 300 megabytes. So that's because the entire file is never loaded in memory effectively. So raw mode, right? That's one of the recommendations that gets given. Is mentioned in the Elixir and the Erlang docs, but it just needs a bit of context. Like using raw mode means that when you open the file, instead of getting back a reference mediated by the file server is a built-in in OTP. There is a process that basically serializes access to the file. You get directly, instead of having that, with raw mode, you get directly access to the IO device that represents the file. If you have to operate concurrently on a lot of files, doing raw mode means that you can do more because you don't go through a single file. However, a reference is a local reference. So the local reference means that you don't interact with the process. The file server would monitor the process that calls the file. So if you don't have that, you have to close manually. When it's monitored, file server looks at the monitoring. If the process that opened the file dies, the file gets closed. And the other thing is, because you're not going through the file, you automatically constrain yourself on operating on a single node. Most of the times it doesn't matter. If you're operating on a file that just, you open it, do some work, and then close it. For example, you want to write it. It's okay if it's in the same node. It's a very short, hopefully, lifespan, so it's okay to use raw mode. But the important thing is remembering that raw mode comes with a certain set of trade-offs. In general, and this is sort of like going back a little bit higher level than the 3 examples, and I didn't add specific pieces of code for that because otherwise it's just too much code in a single place. But whenever you do operations around files that are repeated and not like very simple one-off, like reading a configuration file and loading it in memory, like very simple things like that, with large files, wrap everything in metrics because you're going to need them. Because at some point it will be interesting to see how that behavior performs in production. The other thing which is quite common is that a lot of the times when you want to control the concurrency around this, so say that you want to make sure that your system does not write too many files, doesn't write too many temporary files, you want to constrain that. A lot of people reach out for a pool. A pool normally is for persistent operation. Like a pool is good to wrap a connection because you put it in and out of the pool, and that's a stateful thing that you want to keep. When you operate with one-off operations around files, if the file is closed at the end of the operation, then working with one-off processes that basically start and then stop, so they live and die, it's a safer situation because that will automatically collect references, and potentially you have to worry a little bit less about the garbage collection problem and the memory ballooning. That repository, DuoMark Epoxy, which I believe is pronounced epoxy as a pun on epoxy, has some patterns that could be useful in that respect to look at. It's an Erlang repository, but even just like using a temporary task potentially is something that you would need to evaluate. And the other thing is particularly for memory usage, performing soak testing. So basically produce an automated test that stresses your system over a long period of time. Say like half an hour, 2 hours, 24 hours of operations that stress the part of the system that interacts a lot with files, so that you can see if you are basically leaking memory, if you are doing things that could potentially compromise extended operation. A lot of the times people focus on measuring a peak over a short amount of time that might not show a memory leak that could be extremely subtle, especially if you are testing with, if you, for the sake of speed, you test with smaller files, you're not going to see the same deltas, for example. So soak testing with large files, that tends to find issues that might have gone unnoticed even during like more focused testing or code review. The references around this talk, first of all, like this is always mentioned this book, but I think it's still worth mentioning because it's still the best reference around running Beam in production, Erlang in anger, and Recon from the same author. And then if you want to measure things, I would recommend looking into telemetry packages. So that like if you search on Hex, because they offer, there's a bunch of basically measurements already there, and essentially that gives you the ability to easily instrument your application and potentially funnel all of that information, all of those metrics into a single bucket. If you happen to run an application with a live dashboard, if you use telemetry, you can basically plug all of this in the live dashboard. The one recommendation around is always that if you are worried about measuring things in production, your metrics should go somewhere outside your node. Because live dashboard is good for introspection, but it runs unless you have another node that is connected to the one that you're measuring. But otherwise, you're basically you might not work if you are in a situation where you have a problem because it runs in the same system. So generally speaking, if you can push metrics out, that will help you a lot when you have problems that affect resource usage, because if you have memory, you don't have memory for anything. Any question? Well, thank you actually for listening. Any questions you can sort of like ask now or ping me at the email address shown on screen.
Let's try and give Claudio a closing round of applause, whatever that might mean. Yeah, okay, great. Thanks, Claudio. That's the first time I heard of soak testing. I'm really happy I know that term now.
Don't tell Francesco.
So we have one question and plenty of time. So
yeah.
Matthew, I wonder if you can unmute yourself. I think you should have that ability to ask the question yourself.
Yeah, so I was just wondering, this was all about memory, but how does the speed of writing with that write loop and the stream compare to the original, just the plain writing? Was the speed any different?
For it depends, but it's not noticeable in the majority of cases. I haven't done the exact test for that, for the specific use case here, but in the application I worked on, it's absolutely not noticeable, because you have, it's very limited, the difference between the two. Like you just basically like, you alternate the operation. So it's the behavior of the function is slightly different from the point of view of how the scheduler sees it and the number of reductions that you use before that process sort of like gets deallocated by the scheduler. But in practical terms, you're likely not to see a difference, not in any meaningful term. The one thing which becomes problematic is that you basically get to do more of them because you don't use much memory. So the thing that beat me once was basically not having like running out of my disk quota. So essentially not being able to allocate temporary files not be able to allocate the file for writing because there were too many of them. So it basically there was too much memory available to write there, and so you could write that many files because of memory, but you couldn't because you were running out of basically file operations on the OS. That would get an error around that.